I finally fixed my homemade vibration table, and I got access to software that can run harmonic analyses and random vibration analyses, which means today's video is all about correlating vibration damping, vibration isolation, and vibration analyses. And we're going to use said vibe table to visualize what vibration isolation looks like and correlate some of the vibration effects with our actual test results. Now, I've already kind of covered vibration isolation with the video I made on my FPV mount for my RC boat, but I really only covered modal analyses. I didn't even touch on damping, and we didn't visualize what's going on with isolation itself from a test perspective. We're going to go straight to the technical details here. So this is the component we will be analyzing and testing. It's just a hunk of plastic that's intended to resonate at around 10 to 15 hertz. And then it's going to be attached to this linear table right here that will vibrate it when an input from a reciprocating saw moves this linkage back and forth that reduces the total stroke from like 1 1/8 inch down to about 70 thousandths of an inch. All right, now let's shake things up a little. Now, as I start to move this table at a very low frequency, you're going to see that the mass at the end moves almost the exact same as the table itself, meaning it's a one-to-one transmission because there's no amplification going on. But as we increase frequency, we can see that the mass at the end starts to move a lot more. And that's because it's approaching the first natural frequency and the input movement is being amplified at the mass itself. And now we are at the natural frequency, so I've slowed down the video a lot so you can see just how much further that mass is moving than the base input itself. And that is what resonance looks like. The amount of movement that we'll see at this mass during resonance is a function of damping ratio. With very high damping ratios, this really won't amplify that much relative to the base input, but with low damping ratios, we're going to see this swing a lot further. And I'll talk a lot more here in a little bit about the specific analyses we can run to characterize that, but let's keep going on with testing so we can see what isolation looks like. If I continue to increase the input frequency, we'll see that the mass is no longer being amplified in movement, and it actually appears to almost stand still when we view it in slow motion. This is because we're now entering the isolation region. That means that the transmissibility is actually less than 1. In other words, if I move the base 1 inch, I'm not going to get even close to 1 inch of movement at the end of the mass because it's vibration isolated. Now, I want to introduce you to a chart that compares transmissibility versus the input vibration frequency. On the vertical axis, we have transmissibility, and it's the ratio of the output to the input. In our case, that's just how much further the mass at the end moves than the base input, or how much less if it's less than 1. So a transmissibility ratio of 1 that we saw at the very low frequencies means that the mass and the base are moving together. But when it was resonating, it had a very high transmissibility because the movement at the mass at the end of the rod was amplified to a much greater amount than the base input. And then it was the exact opposite whenever we were isolated and the mass was barely moving relative to the base input. And this is exactly what I was doing with the FPV camera mount on my RC boat. I was isolating the camera itself from the base input vibration with those 3 little silicon vibration damping balls you saw between the camera mount and the base. Isolation frequency is theoretically defined as the natural frequency times the square root of 2. And with that, we are now ready to take all this awesome new knowledge and run some vibration analyses. I'm going to be using Inventor Nastran, and they call it something like a Modal Frequencies Response Analysis. But ANSYS and SolidWorks both call it something like a harmonic analysis or a harmonic response. I don't remember the exact verbiage. Regardless, they all basically characterize the response of a system to a sinusoidal input. And in our case, that input is displacement of the table with an increasing frequency. But you can also use acceleration and force and other types of loads to run the same analysis. It just depends on what you're actually analyzing. From this analysis, I can pull stress at a given frequency to understand how much of an impact resonance and isolation have, or I can view graphs that show me the transmissibility at a given point. This is very useful in understanding how different regions of the structure respond to vibration, and also if I want to compare how different damping ratios affect the dynamic response of a system. And on that note, let's go compare some different damping values and see how it affects the response of the mass at the end of our test piece. In this first example, I've only got 2.5% damping, and the max stress at resonance is 841 psi. If I increase damping to 15%, this max stress goes all the way down to 140 psi. So more damping, more better, right? Wrong. Sometimes. It really depends on what your input vibration profile looks like. In the case of my RC boat, below 20 Hertz, it's pretty low amplitude, but above 40 Hertz, it jumps in energy quite a bit. So let's compare what transmissibility curves look like between 2.5% and 15% damping on our test piece. We can see that the transmissibility is way lower at resonance for the 15% damped case. But remember that the vibration profile for the RC boat already was pretty low energy in this frequency. But if we look at the transmissibility above the isolation frequency, we can see that the 15% damped case is always higher. And the higher the damping you have, the higher that gap is going to be between a lower damped value. So when it comes to our RC boat camera mount, that means that the higher the damping value we have, the more of this high frequency energy we're going to transmit to the system. I'm not saying that the 15% damped case is worse. To understand which is truly the best case, we would have to run something like a random vibration analysis, but we're definitely not doing that in this video. That'll come at a later time. Let's continue on just understanding the basics of damping and isolation. Now, if you're wondering where the damping ratio or damping values are defined and controlled, it's usually in either material selection or the assembly selection. Metals generally have really low damping, like they can be below 1% damping, and some rubbers can be above 20% damping. So silicon is a very common material to use for damping, as well as some other types of rubbers. And if you're looking for off-the-shelf vibration isolators, they'll usually publish what the damping value is. And they'll also publish a range of temperature options and all that. In the case of the FPV camera mount, I used off-the-shelf little silicon vibration damping balls. That was a combination of cost and understanding that this was a good trade-off between a medium damping ratio, but not over damping my system. You can also use friction to damp things, so wire rope isolators are a good example of this, and other slip plates will damp a structure inherently. Now, if you want to see a super fast overview of how I set up a Modal Frequencies Response Analysis in Inventor Nastran, let's go. First, we create a new study and select Modal Frequencies Response. Then you select the acceleration box in the output controls and hit OK. Create a new idealization of the part if you haven't already done so that you can create a mesh. And you want your mesh to be fine enough so that it can get good resolution for the results, but not too fine because these studies take really long. Next, you're going to set your damping values. Your damping values are based on material. Here, it's 2.5%. Hit OK. After this, we go into our modal setup where we're going to define our minimum and maximum frequencies for the study so that we cover the entire range of interest. After that, we're going to add a load, and in our case, this load is going to be an enforced motion. The exact enforced motion type is going to be selected as displacement, and we're going to apply that displacement to the feet that are mounted to the table on the bottom of the unit. We're going to set that displacement to 70 thousandths because that's how far our table moves on each stroke. Next, I add constraints to the exact same faces that we put the enforced motion on, and we call those fixed so that it treats this load as a base excitation. Next, we go to the dynamic setup to define a frequency range, and we're also going to define the total number of points in that range. After that, I'm selecting the option to spread around each mode, defining the minimum and maximum frequencies again, and the total number of points to spread around each mode so I get concentrated data in a modal response, based on the percentage spread. And then all we have to do is select Run. I can add new plots when the results are done by selecting XY plot, going to the node that I want to pull results from, selecting that node, and making sure to select the exact results I want. I want displacement in this case, so I'm just going to show XY plot, and this is the data I get. If I want stress results or anything else like that graphically, I select the frequency that I want, go into display, and it's going to show me the stress or displacement or whatever it is I care about for that frequency specifically. Now, this is a video I've wanted to do for a really long time because it would have personally helped me a lot to see something like this early in my career. So I really hope you found it as useful as I think it is, and if not, lie to me. I also want to point out a few other things. Number one, If you get the damping ratio wrong in these analyses, you could have some very negative results. So definitely don't cheat or guess here. You should really kind of understand a general damping ratio that you're going for. Number two, this is just scratching the surface of vibration analyses. It's actually a really complicated field. So I encourage you to dig deeper because it's also a really cool field and something that can take you a lot of places in your career. Number three, there are a lot of ways to run different vibration analyses, so I'm definitely not saying this is the only way or the best way. It really depends on your application and what exactly you're trying to understand. And four, I'm sure I'm forgetting a lot. So again, either feel free to ask me questions or research yourself and look at what else is out there. Thanks everyone for watching. Hopefully it's as useful as I think it is. And if it is, please like and subscribe. And if you really even think a friend could benefit from it, please share this video with them so they're not in the situation like I was, trying to piece together different fragments of information and taking way too long to understand what damping and isolation really meant. I promise the next video will be a lot more fun if you care more about projects than technical stuff, but I really wanted to get this done. So keep an eye out for more fun stuff. Thanks again, and we'll talk soon.